Alright, where are we? I believe we are starting Gabversity. We are. Where facts care not about your feelings. It's actually starting to heat up, so I may have to take off this jacket soon. It's a bit hot here. I think I might have to do it. James Joseph, the whole family is here. I don't know why I would say that every time. I would say the whole family is here. It is very hot because it is spring, even though it feels like summer. Hey, all right, let us begin, my friend. So the first one, the Crab Nebula, sweaty big dicks. Wrong timing, my friend. You were doing so well. All right, so the Crab Nebula, which is now about 1 parsec in radius, which is about 3.24 light years in radius, right? And it's the remnant of an explosion. Do you live in a mansion? Hey, how goes it? It is great, my friend. I hope likewise for you. All right, now it was actually observed by our ancestors. Our ancestors saw the Crab Nebula explode, right, in 1054 AD or CE, whatever you want to call it. 10. You're a rich guy. I'm rich with my Periscope supporters. Yeah, it's pretty good. Apart from that, I have nothing. All right, so Wheat the North Star in the stars. Where's the North Star in the stars? All right, so we've got here 1054 it exploded, and now it is about 3.24 light years in diameter. Assume a constant expansion rate. Okay, well, the distance is 1 parsec. So let's have a look. We want to know the rate, right? So yeah, I can't even see what I'm doing. All right, the rate. We know now that it exploded at 1054 AD. How funny, 1054, isn't that when like the East and West Roman Empire split, the churches, the Christian and the Orthodox, Catholic and Orthodox split in 1054, I think, wasn't it? The East-West schism. That's the same time as the explosion of the Crab Nebula. What a coincidence. All right, and then up till 2012, what's that? That's, but I bought your book and it was a really interesting read, can relate. Oh, wow. Thank you very much. That's awesome. I'm glad you enjoyed it, my friend. That means a lot. All right, so how many years do we have in between these two? Well, it's 958 years. Okay. So over 958 years, the Crab Nebula went from this to... And that is like 1 parsec across, which equals approximately 3.24 light years, which equals approximately, what's that, 3.1 by 10 to the 16 meters. All right, so that's 3 with 16 zeros. 3 with 16 zeros. And I'm glad that you guys love the book. That is so cool. Where are we here? Abyss and Scott. We've got Abyss and Scott left today. It must be really, what time is it for you guys? 9, it must be like 7:30 p.m. Between 4:30 and 7:30 p.m. for you guys. All right, so we know that the distance it has traveled since 1054 CE/AD is 3.1 by 10 to the 16 meters. That is a long distance. Very long distance. So if it's traveled that far, and 1 year is 3.2 by 10 to the 7 seconds. Where are we here? The time. Okay, so 3.2 by 10 to the 10 seconds is in 1 year. 10 to the 7, sorry. And there has been between 1054 and 2012 around 958 years. So call it about so if you add that on, 3.2 by 10 to the 7 seconds multiplied by 958 years is going to equal about 3.5 times 10 to the 10 seconds. 3.05, sorry. I knew that it wasn't a complete 1,000 years. Yeah. So you're talking 3 with 10 zeros. So that's like 30 billion, 30 billion 500 million seconds. And then you divide them. So if you divide the distance over the time, you're going to get 1,000 kilometers per second, which is how many miles per second? It's about 620 miles per second. So it turns out the Crab Nebula, the average speed since its explosion during the East-West Schism of the Roman Empire, or the church, sorry, the East-West Schism of the Christian Church, Genetex and hey, is 620 miles per second, and it has been traveling that long ever since. So it's traveled 3.24 light years. That is just insane. It's traveled so far that there is no way it can communicate with its other side. It would take like at least 6.5 to 7 years to get a message at the speed of light from one end of the Crab Nebula to the other. So it's not even a thing. I don't even know why we call it a thing. Like in 4 dimensions, it would not look like that. Crazy. So the initial explosion was probably really rapid. So I don't think that that's actually the rate that it's been traveling. It was probably traveling at like, I don't know, like 5,000 miles per second. And now it's traveling at like, I don't know, like 100 miles per second. I don't know. I'm just saying it must have been like, it's been decelerating ever since. So the average has been 620 miles per second or 1,000 kilometers per second. But that's not really what's been happening the whole time. And it's also colliding with interstellar medium, with gravity playing almost no role, believe it or not. So it's just as the cloud explodes, right? It's just smashing into other stuff all the time and slowing down. So there you go. That is one question done right there. Let's have a... my arm is freaking killing me, and that is not a dirty joke either. So the next question is, a supernova's energy is often compared to the total energy output of the sun over its lifetime. Using the sun's current energy output, calculate its total energy output, assuming the sun has a 10 billion year, or 10 to the 10, main sequence lifetime. How does it compare to energy released in a supernova? Alright. So all we have to do is get the sun's luminosity, alright, and times it by the number of seconds in the sun's 10 billion year lifetime. Alright, so the luminosity of the sun, right, and I'm pretty sure it's per second, is 4 by 10 to the 26. So its luminosity is 4 by 10 to the 26, which has to do with its surface temperature and has to do with the area of the sun. So what's that? 4 by 10 to the 26. That's 3 nines. What's 3 nines? 27. So it's not a triple billion. It's 100 million billion billion. So 400 million billion is the sun's luminosity per second, and there are 3 times 10 to the 7 seconds supposedly in a year, multiplied by 10 billion years. Why not minutes and hours? Did question require it? Good question. It does require it because we're converting it into joules, so we're just shoving them all down into the right energy output and then moving it into joules. But you're right, you could have done an equivalent, like just use hours or use months or years. It's the same thing, yeah. So when you multiply them together, you get 1.2 by 10 to the 44 joules. 1.2 times 10 to the 44 joules. All right, so what are we saying here? We are saying how many joules does it take to heat up 1 gram of water 1 degree? I think it's something like 4.4 joules. And this is 1.2 by 10 to the 44. which is 5 nines are 45. So it's, what would you call that? That would be 100 million billion joules. Yeah, that's a lot of energy. All right. The supernova gives off 1/10 of that. So basically a supernova gives off 1 billion years of the sun's energy. So what the sun gives off in 1 billion years is what the supernova gives off immediately in one explosion. All right, that's ridiculous. I don't even understand that. I just got a message from one of my colleagues at work. Let's see what's going on. I'm trying to best this on this. What do we got here? Fuck. Sorry, they're going to be away for a bit. That is so disappointing. All right, I've got to deal with that. I've got so much to do, man. You know, I hate that. Mad ass letdown. Gonna have to find another assistant, I think. Anyway, when a supernova explosion occurs, it rapidly ejects a vast cloud of gas, and this is called a supernova remnant. Supernova remnants can last for thousands of years and provide evidence of an earlier supernova, which is good for us, I guess. We see many of these structures around the galaxy, such as the Crab Nebula, which we just spoke about, right? We also see all around us very complex elements that are typically created in supernova explosions. And those two things that we see are evidence that many supernovae have actually occurred in the Milky Way. In a reset. All right, next. By the way, big love to my Patreon supporters and those who have bought the book. So it's starting to get more and more. So Abyss, and Dave and Scott, thank you. And it is because of you that I can do so many scopes. You remember the 1986 supernova. My friend, you have an excellent memory. If you can do that, geez. All right, so what proof do astronomers have that heavy elements are formed in stars? Well, there are two lines of proof. First, the abundance of the elements in the universe varies greatly with atomic number, in a manner that can be predicted by models of supernova nucleosynthesis. Okay, so they're exactly consistent. Hey, speaking of Patreons, L. Brooks. Second, the decline of a supernova's light curve after the explosion is consistent with the afterglow that comes from the decay of complex radioactive elements created in the explosion. I don't get that. Hold on. The decline of a supernova's light curve after the explosion is consistent with the afterglow that comes from the decay of complex radioactive elements created in the explosion. Gotcha. So the radioactive elements are created during the explosion and then they're decaying in space. So that would explain why there's so much bloody radiation in space as well. Okay. How are nuclei heavier than iron formed? Nuclei heavier than iron are formed by neutron capture. Okay, the nucleus of an element captures one or more neutrons, which have no charge and thus no electromagnetic repulsion. Once attached, the neutron can decay into a proton, forming a new, heavier element. This process can proceed slowly inside of massive stars, the S process, or very rapidly during a supernova explosion, the R process. All right, that's interesting. So they just wander in. So how we go? The nucleus of an element captures one or more neutrons, and they don't have charge, so they just sort of like go right through the electromagnetic radiation, the electromagnetic repulsion. That's funny, eh? There's like a magnet, and they just wander through, no problem. Once attached, they decay into a proton. Gotcha. So it actually goes into a proton, then the actual element changes. That's so awesome. I love that. All right. Next. Speaking of your excellent memory, who was that who said that? I can't remember. It was someone with a name with G in their name. but it doesn't show up. It's weird because your periscope nickname is different to your periscope handle. Anyway, so the Gentleman Ghost. I want to see what your actual name... JK. That's why I couldn't see you, because it shows up as JK. Yeah, Gentleman Ghost. So the supernova 1987A is the closest supernova to Earth in the telescope era. It wasn't in our galaxy, but it occurred in one of our satellite galaxies, so one of the smaller ones that orbit us, I'm guessing. It's called the Large Magellanic Cloud. 1987. Still pretty good to remember. This made supernova 87A very accessible and easy to see. Hey, Kevro is back. What do you know about black holes? I was going to make a dirty joke and I decided against it. I just got a new job, did I? The distance to the LMC is very well determined, so astronomers could immediately determine its brightness and total energy output. It's very little dust between us and the Large Magellanic Cloud to obscure our vision. Lastly, since we could track down exactly where the explosion came from, we could locate the star that exploded from archive photos. That's pretty cool. For the first time, astronomers had observed the star and knew its basic properties before it exploded. That would be pretty cool, because then you can measure what you assume the star would be after the explosion and then check whether you were actually correct. It will continue to be a very important supernova for a long time. Progenitor stage completely, I think Banter just showed up, completely through its development as a type 2 supernova. Are we talking about dwarfs and stuff? Yeah, like I have a cousin who's a dwarf. A brown dwarf. Hey, Banter. Alright, so let's have a look. Once the core of a massive star becomes neutronized, what the F is on your head? It is a hat. We do have those in West. They are predicting a supernova in 2022. I'm not kidding. Cool. Okay, I'll have to see that. Once the core of a massive star becomes neutronized, electron degeneracy pressure cannot fight gravity anymore. Gotcha. And the core goes into free fall. Yeah, because just okay. Because it becomes so dense that gravity just grabs it, crushes the bastard. The collapse is only stopped by the onset of neutron degeneracy pressure, which is freaking phenomenal. That happens on a quantum level. Physically, the computer program that we live in, called the universe, does not have enough pixels to allow the neutrons to keep compressing, so they stop. How funny is that? They stop. They just stop, because if you squeeze them too much, there's not enough pixels. It's almost like the computer that supports us runs out of RAM or something, so it just stops. That's how freaking universe, man. It's just, that stuff, it blows my mind. Yeah. The collapse is only stopped by the onset of they call it neutron degeneracy pressure. And all that means is that the neutrons can't squeeze any further. And exactly what I was just saying, no one knows why. It's just that it just happens that way, right? As the resistance of neutrons to being crowded together opposes gravity. As the core stops collapsing, the rest of the layers of the star rush inward and rebound from the core. So they collapse in and go and bounce back right off. Thus the explosion begins with an implosion. Okay. The shock waves from the outer layers colliding with the core and each other create the explosion. Okay. It would be quite phenomenal. Entanglement blows my mind, how the information communicates instantly no matter the distance. Yeah. Well, I'm going to be talking about that in my quantum mechanics lectures, but I'm going to be talking about how solids actually exist first, and then we'll get into entanglement later on. If you've done so many uni calculus, but it's quite fascinating. Yeah, absolutely agree with you. Both types of supernovae are explosions but look different from each other. This is type 1 and type 2 supernovae. Type 1 supernovae are observed to have hydrogen poor spectra and slightly fainter than the type 2. Okay. They also fade much more quickly than type 2. Type 2 have strong hydrogen lines in their spectra, get a little brighter at maximum than type 1, and then their light lingers on for much longer. I thought type 1 was bigger, so it sounds like type 2 is bigger. Okay. What is the Chandrasekhar mass or limit? Chandrasekhar. And what does it have to do with supernovae? The Chandrasekhar mass is the limiting mass for a white dwarf. 1.4 solar masses. If a star will explode. That's not a bad guess. Well, you know more than me already. I didn't even know. I'm just reading it now. It says it says if the mass exceeds the limit, electron degeneracy pressure can no longer hold up the white dwarf. The dwarf will collapse, resulting in a supernova explosion. There you go. JK is on the money. As atoms fuse on a massive scale, a white dwarf can exceed the limit in two ways. Number one, it could be a binary system, accreting matter from its companion. I've heard about that. It's like it's sucking matter from the other star, and then it gets too big, so it just explodes. Alternatively, the white dwarf could begin above the limit as the core of a supermassive star. Okay, yeah, that's an easy one. All right, let's look more about the difference in type 1 and type 2 supernovae. Type 1 supernovae occur when a white dwarf in a binary system accumulates enough mass from its companion to exceed 1.4 solar masses. Okay, so that's the type 1 type. Once the mass exceeds that limit, the dwarf will collapse. Can have enough mass to explode. A dwarf star. There you go. Don't mess with the dwarfs, huh? Gravity forces the carbon atoms in the white dwarf so close together that they must all fuse, creating a huge detonation. So it's basically like a nuclear bomb. Okay. What have I got here? Under what circumstances will a binary star produce a nova? A nova is a binary star system that suddenly brightens and then slowly fades back to normal. It's caused by an evolving star in a binary that is expanding past its Roche lobe and losing gas to a companion white dwarf. Gotcha. Okay. So it's the same thing that we just spoke about. The material, primarily hydrogen, builds up on the white dwarf, reaches a high enough temperature to fuse. Brief reflection of light from the surface of the white dwarf. So that's just a nova, that's not a supernova. What is an accretion disk and how does one form? An accretion disk, I'm guessing the accretion disk is sort of like when, you know, when water goes into the bathtub and it sort of swirls around. It gathers material from the outside source. The material does not fall straight down but forms a flat disk as it spirals inward. Yep, there you go. So that's what we were saying. What is a light curve? A light curve is a diagram that plots the changes in brightness of an object. Since dark matter interacts with gravity, it should fall into black holes, I think. You'd think so, right? But so far no one's been able to detect whether that actually happens or not. Only the water is gravity. Water? Oh, no. I was just giving a hypothetical, an analogy, saying water in a bathtub spinning around. A light curve is a diagram that plots the changes in the brightness of an object. Hey, by the way, your Twitter, I went to go see your Twitter and they bloody suspended you. Which, I'm sort of half not surprised because your line was, I own 27 guns. I love that line. It's so funny. It's just so random. A light curve is a diagram that plots the changes in the brightness of an object as a function of time. Okay. But does the accretion disk spin rotate? Yes, it does. It does rotate. And I reckon it probably rotates for two reasons. One is as the rotation of the object itself causes it to rotate, as well as the initial rotation as it's traveling inwards. So it probably makes massive turbulence. Try Jenny the G. Yeah. Alright. Time is plotted on the horizontal scale, brightness on the vertical scale. So the light curves of novae, so that's a four-dimensional luminosity view, that's what they're saying. The light curves of novae and supernovae appear rather different. Supernovae are known to brighten about 1 million times more than novae. Arguing politics. I'm sorry to hear that. The patterns of brightening are also different. Novae brighten and fade. I have this tweet on my Gab. I think it's on my Gab Smacked tweet on my other Twitter account, and I say something like, "I believe in a maximum wage, but that doesn't make you a racist." For example, supernovae are known to brighten about 1 million times more than novae. The patterns of brightening are also different. Novae brighten and fade less drastically and more gradually than supernovae. All right, so novae are sort of like the sane boyfriend. The supernovae is like the crazy bitch or the crazy guy. You know, why does the core of a massive star collapse? I think we've done that one already. Oh no, that's the last one on this chapter. So why does it collapse? Well, we spoke about this actually in one of the other episodes. If a star is massive enough, it will be able to fuse nuclei into iron, thus building up a core of iron. But due to the high amount of repulsion iron atoms experience, it requires more energy to fuse iron with something else than the reaction releases. This actually decreases the amount of energy available. So it's like a human turning into stone. It's like that, something like that. Nuclear energy generation stops, and as the core collapses under gravity, it cannot produce additional energy to stop the collapse. And there you go. The whole thing just shrinks. That's just crazy. Stuff is crazy, my friends. 32 gigs. Welcome back. I think we're done. I think we've got a few more questions and then we're out of here. Then I'm going to go to quantum mechanics. Do all stars eventually fuse helium in their cores? A star must have sufficient mass to collapse its core, enough to reach the critical temperature of about 100 million K. I'm so excited that Abyss read my book. You have no idea. Like, I love that everyone reads my book, but Abyss is like, he is my Liran. If anyone's on my original Gabsmack channel, I have this one guy called Liran who's very similar to me in the questions he asks. Like, he would ask me questions I would ask myself, and Abyss is sort of the equivalent on my quantum mechanics. So the fact that he read my book, it's quite an interesting experience, because he would ask me questions I would ask of the author if I read the book. All right, a star like the sun. A star must have sufficient mass to collapse its core, enough to reach the critical temperature of 100 million Kelvin to fuse helium into carbon. Only stars with a mass more than about 25% of the sun's mass can manage to do that. Okay, so in other words, anything that's 1.25 the mass of the sun or less will not fuse helium into carbon. It'll stop at helium. All right, so you know what? Look, this is what I mean. We as humans, I'm certain, could use the harness tech recommended just goes to so I'm here, blame him. Abyss, well, thank you and not thank you. No, it's great. I love sorry? Okay. Okay. Alright, I gotta go take the Arabic coffee to my mum. So I have to go. But it was lovely to see you guys, and pleasure to meet you, JK and Abyss and Slim Grady's back and everyone. Love you all. And we'll probably do some astronomy later and some quantum mechanics. Mwah, facts don't care about our feelings.